So what we did last time is, we have dealt with the expectation of the indicator function and the step function, right? The expectation of step function, correct? That is what. So this we define the step function and then we have defined the indicator of the step function. So uh, yeah, X is a random variable. Then what about where? Yes. Sorry. So, so X be a random variable. Then what about then this expectation of h of x? Okay. This is nothing but integral over r h of x d. This is the another thing. I mean, so we have defined what is the expectation for a random variable. Now it's a composition of function h of x. Okay, so if you have so the it is more precisely you can write like dp. I mean this one. Okay, so this is the thing, and also I mean, if you have a density function, so it is also can be written as h of x, right? Fx x dx. Right. This is the density function. So this is the density. Right? I mean, whenever x is a x is a random variable which has density, then sorry, then this is the definition of the thing, right? Because you see, for any random variable, what is my definition of this thing? It is integral over omega x omega dp omega. That way you can write, right? Uh, so yeah, but here h is a function from r to r, so the integral will be over r, and the integral over r dpx. The dpx is nothing but the yeah, so that is what we have defined earlier, right? I mean, um, for example, yeah, so you see, uh, this is my definition of uh, for this thing, right? This is my definition of so if you take dp both sides, this is nothing but fxx dx, right? That is the uh, what you called yeah, like we have done it here. Uh, the density function or whatever derivative of the distribution function is nothing but because uh, because you see what is the so this is the so I what I have is this is nothing by definition is fx of x, right? This is my definition of the distribution function. So yeah, you can so in a sense that yeah, you can write it like this. This is now how to prove this thing. I mean, for this is and for we can so this is for the continuous random variable. For discrete, for discrete you can write is equal to summation h of xi probability of x equal to x. Right. This is my sum over. So this is my discrete random. For discrete, it is the sum for continuous it is the integral. Now, how to prove this thing that this one? How will go about it? So yeah. So how will you go about it? Is uh, you have to so yeah. So first we can what we already know the for what we have already learned is the if it is a step function, then we have evaluated what is the this thing, what is my the way you look at the you calculate the expectation. So we do it for the step function because that is what we have done, right? So let it is a step function. This is a step. So, eight. So step functions, how it looks like we have discussed last time, right? This is my picture of the step function. So it is like h equal to h1. So x if x is in a1, then here it will be h of x, right? That is my this thing. So in a sense, so so here you will have, I mean, h of x, right, is h1 x in a1, h2 x is in a2, hn. I mean, you can be more precise. This is h1 of x. I mean, you can have h2 of x like that. So this is my step function, right? And these AIs are pairwise disjoints, right? So AI intersection HA is in T set for I not for I not equal to no. So for I not equal. Now now what about when H is a step function? What about expectation of n? What is this? Is equal to summation I equal to 1 to n hi, right? Hi uh, indicator AI. Right? Uh, so sorry. So I mean, how will that? So so we'll write it like this. So expectation summation of n hi indicator. I mean, uh, Now, as we calculated, this one is equal to summation I equal to you transfer the expectation with this thing, so you will have summation I equal to 1 to n hi, right? X belongs. Right? And so this is uh, this is this is just you can just rewrite it like this. This is so this is I mean this is what this is nothing but you take the probability measure over the AI. So, so in a sense that you can write it is over. This is just I mean this is the probability measure of the set AI. Right? This is the probability setter of the set AI. I mean, for example, if you just simply take one example, right? So suppose you have integral over R, indicator function, okay, 0 to t, okay. Yes. So what is this one? Integral, it's a, just time interval, integral over 0 to ts, indicator function 0 to ts ds, over integral over the whole R. So this is function is over 0, indicator 0 to t. So in a sense that this is nothing but 0, sorry. So this is nothing but 0 to t ds, right? And this is nothing but t. This is nothing but t, right? So, so in a sense that I am writing this probability measure I mean, similarly, suppose I have something like this, mu of A, measure of a set A, correct? So what is this? This is nothing but integral. Suppose you take over the whole R, indicator of X d mu of X, right? Because when you take the indicator of a set, that means it is one over the set and zero otherwise, right? So measure of any set, you can always write it like that. We integrate integration over R, indicator 1x t mu x. In a sense, because over A it is 1, so integral over so basically this is again you can write it equal to, so you can again write it equal to integral over A. So so basically A intersection R, right? Whenever A intersection R d mu x, right? And so this is nothing but indicator of d mu x. And this is nothing but mu of it. I mean, that is what happens, right? So we just use that here. And yeah, and yes, so this is, and what we have taken is the h is the uh, step function, right? So h is the step function. So and AI is a disjoint. Correct? So so this is, so h is I mean h is over only over these things, right? I mean, so in a sense that you will have so AIs are AIs are Borel sets, and union I equal to 1 to n, AI is equal to R. So this is the partition. So it is the partition of R. You just make this partition. Yeah. So you'll have yeah. I mean, the step function is, I mean, we have taken it like this, G1, A1, A2, A3, and whatever the outside of AN, I mean, the outside of AN, that can be considered as zero. I mean, there is nothing there. So if you take the whole real line, because over the AI, any union of AI complement, there is nothing, I mean, there is zero. So in a sense that you covered the whole this thing. So therefore, this is over integral over AI. So, and you take I equal to 1 to n. So in a sense that you just write it over integration over R, h of x d. So so this is expectation. I mean, this is the proof when h is a. So we started with h is a step function, right? But we have to prove this. We are stating this for any general x. It is not for any Borel function. Any Borel function I am talking about. Okay. But I proved that the result for when h is a step function. Okay. So this is first step, and then next step. I can write next. Consider H is a non-negative Borel function. We have to prove it for H any Borel function, but first is non-negative Borel. First is H is can be observed by non-negative non. Next is we consider non-negative Borel function. Now, anything you are hello? Sorry, you are talking. You are saying asking anything? Please be loud. Hello. Okay. So H is a non-negative Borel function. Okay. Now there is a property that a result. Okay. So there is a result that H. I mean, when it's a non-negative Borel function, H can be approximated by a sequence of step functions. Sorry. Hmm. Actually, the general proof requires little bit more on measure theory, which still now you don't have. Uh, Still now you don't have. Okay, so I would say. mm, okay, I just give a brief description this part. So main thing, whatever you have you learned, this part is clear that if h is a step function, then expectation of hx equal to this. This is there is no issue. But to go for any general Borel function, there is a little bit of measure theory involved, which still now you did not have it. So this part, I just say, you don't have to worry about this part. Okay. Uh, So H can be approximated by a sequence of step functions. So any non-negative Borel function you can have, it can be approximated by a sequence of step functions. Okay, and so in a sense that, I mean, H, you can write it as, I mean, H of X can be written as limit n goes to infinity Hn of X. Okay, so where Hn, so this is a sequence of step functions. So you see what we are trying to say, that this is non-negative Borel, uh, non-negative Borel function, right? And this limit is pointwise limit. So this limit is called pointwise limit. So in a sense that you have this, so you can, this result is there. Uh, any non-negative Borel function you can approximate by a sequence of step functions. The moment you do it, then what you have to do? So we have to do the expectation. You have to take the expectation in both sides, right? So sorry. So in a sense, so from here you integrate over that is what I have to do, right? This is my expectation of it. So this is integrating both sides. Here is sorry. I'm just taking integration is over R, limit n goes to infinity h on x dx. It is just integrating both sides, right? Integrating over R both. Now there is a crux here. The crux is this integration and limit. This integration and limit. And what we can actually do is we can change the integral with the limit. So in a sense, we can write limit n goes to infinity integral over R hn of x dx. Okay. And these integral with the limit, this is here is the major theory comes. I mean, you cannot always change this thing, and here you need certain convergence theorem. It is called the convergence theorem. It's mainly you have to use some monotone convergence theorem or bounded convergence theorem or dominated convergence theorem, whatever it is. So you have to use some convergence theorem here. This for this inequality, you have to use some convergence theorem. This part is from measure. So once you do that, then you can write it is equal to limit n goes to infinity. This is nothing but expectation of Hn uh, Hn of x, right? And here is expectation of sorry. So this is from, I mean, this left side is nothing. So in a sense that you can have this type of thing, and so for non-negative Borel function, you can do like this way, and for general Borel function, this h, I mean for any Borel function, h of x can be written as h plus, right? H plus minus h minus, right? So I mean for any, I mean this is a general thing for this thing. I mean h plus and h minus is always greater than 0, right? I mean h plus definition is maximum of h h plus x. This definition is h maximum hx 0 and sorry h minus x by definition is but the h minus definition is having h minus is maximum. Remember correctly. I think this will be the definition of h minus maximum. If I remember correctly, this is the definition. Either maximum or minimum. I'm just forgetting. Yeah, whatever we have written is correct. It's my maximum. I mean, you can write it in this way, or you can also write it minus of minimum of hx0. I mean both is correct. You can write maximum of minus hx0 or minus minimum of hx. So if you see this, this is maximum of minus hx or zero. If minus hx means negative, so zero is the maximum. So h plus h minus is always positive, right? So or non-negative. You say better is the non-negative. And for non-negative Borel function, you have this proof. Okay. So so first you do it for step function, from step function to non-negative Borel function, and for then any Borel function which can get decomposed in two non-negative functions. So any Borel function can be decomposed. This is decomposition in any, can be decomposed in two parts, two non-negative parts. That's the important thing. Any Borel function can be decomposed into its positive and negative parts, and both are non-negative. So in a sense, now you can so in a sense that from here you can write expectation of h of x is equal to, you see, expectation is linear, right? So expectation of h plus x minus expectation of h minus x, right? And these both are non-negative Borel function. Negative Borel. So therefore we can use this part. So anyway, so this part actually, that's what I mean. This part you need little bit measure theory, but up to this point you do not. I mean, whatever we have learned, you can do it up to this one. It is a step function. You can prove this one. So yeah. Okay, we take a 10 minutes gap and then we'll sit. Okay.
Okay, sir.
Another 10 minutes gap. Hello? Hello?
Yes,
Yes, sir.
No. Okay. Yeah. So, so we have talked about expectation. Now we'll talk about variance. Okay. So variance. Yeah. We'll talk about variance, which is now how you do the variance. For variance, so for expectation, we have talked about uh, just a moment. Yeah. So, so now we'll talk about variance. Okay. So so for expectations, we have seen the L1 integrability condition, right? I mean, we have defined that what is an L1 function. Right? Yeah. The family of integrable random variables is denoted by L1. Right? And because if you see, so this is the integrability condition, that expectation is the way it is defined. It is integrability condition, and it is the definition of L1 space, right? It is integrable. Now for variance, we need something called L2, so square integral, right? So, so in a sense, uh, square integrable. So you can also this is equivalently we write integral over omega x omega square dp. Omega is fine. So this is called the square integral. So what is the integrable is mod x dp finite, and it is square integrable if it is mod x square dp. Then the variance of random variable is defined as integral over omega, right? X omega minus expectation of x omega is whole square. So this is the definition of variance. This is the I mean, expectation of x omega, we have seen how it is, and variance of x is x omega minus expectation of x omega. Let whole square. And similarly, the family of uh, square integrable variable is denoted by L2. Or someplace, or you can just write it as L2. In some book, it is also written as L2, right? I mean script L, right? I mean, whatever. Uh, so so this is the family of square integrable. So now Now, there is also one important inequality. It's called you can call Cauchy-Schwarz inequality. Mm. Cauchy-Schwarz inequality. So Schwarz inequality. I mean, it has different forms, but there is something in the expectation form. So that is expectation of x y. Uh, uh, you can have both way. I mean, you can have this whole square is less than equal to expectation of x square into expectation of y square. Okay. So this is one form, or also equivalently, you can have expectation of xy less than equal to expectation of x square whole to the power half into expectation of y square whole to the power. I mean, anything is okay. I mean, So this is very important inequality. It will be used in many places. It's called the Cauchy-Schwarz inequality. Uh, and we will have and there is a nice application to it. There is a nice application to it. So we can have an application. If X is L2, or X, or we can write it more mathematical way. Let me write it X in L2 omega F T, right? Uh, if not required, X belongs to implies X is one. This is the you can apply. So X is in L2. That means X is in L1, not the other way around. Okay, this is important to me. X is a square integrable. If X is something is square integrable, then X is in L1. So, so you see, yeah, in a sense that we know something, right? Suppose a element X belongs to A. If X belongs to A implies X belongs to B, then we can write A is contained in B. Right? That we know, right? If we prove, but I mean, how to prove A something A is a subset of B. If X is in A implies X is in B, then we can write A is contained in B. Right? So similarly here, it is uh, that L2 is contained in L1. And so this is for the this is to be noted that this is for this probability measure. I mean, this L2 is contained in L1. This is for finite measure. So because probability measure is a finite measure, so this will hold. Okay. So this is for I mean, this this is some sort of embedding, or this is an inclusion. So L2, I mean, so here it is not this result L2 contained in L1 is not hold for any measure. Okay, that is more important because you have a probability measure, which is a finite measure. This results hold. So therefore, this probability measure is important here. Okay. Uh, so if X is a square integrable random variable, then it is integrable. Now, how will you prove this from the uh, by application of Cauchy-Schwarz inequality? It's a simple proof. I mean, this is just almost one line proof. Can anybody see the proof from Cauchy-Schwarz? Can anybody notice what is the proof? Hello? Can you try?
Yes, sir.
Yeah. Tell what you want to try. Class. ক্লাসে পর যাব আমার ডিজিটাল এসেছিল ওখানে যেতে পেলে তাহলে একসাথে যাবো কটার সময় ক্লাস কমপ্লিট হবে 11:50 আর 12:10 ফাইন আমি ডাল ঠিক তাহলে তুই ল্যাপটপটা নিয়ে নিস আমি আর ল্যাপটপ মেলটা দেখাতে হবে আমি ডাল sorry. Okay, so anybody want to give it a try? So what we have to prove? What we have to prove? We have to prove that something is L1 integrable, correct? L1 integrable means what? That L1 something is in L1 means integral over omega x dp finite, right? So in a sense that this is nothing but expectation of mod x finite, right? This is we have to prove. Okay. This is we have to show. And what is given to you? What is given? Is it is L2 integrable. So it's given that x square, this is finite. This is given to you, right? L2 integrable means this, right? This integral over x omega. So this is nothing but x omega. So this is given to you. This is given. Right? Correct? Clear?
Yes, sir. So then we can split, sir, like e की power x is mod x square equal to yeah, two parts, sir. We can split.
Yeah, that you can do. That you can do. But okay, whatever you were telling, let's do that. So you are telling that expectation mod x square. This is finite. So this you want to split at mod x. You want to do this?
Yes, sir.
So now you want to apply Cauchy Schwarz.
Yes, sir.
So if you apply Cauchy Schwarz, what will be expectation x square whole to the power half, right? This is my Cauchy Schwarz, right?
Yes, sir.
Now this is my Cauchy Schwarz, right? That is what you wanted to do. But from these, what we know expectation of x square. We have this thing finite. So we have, so this will be finite. This will be finite. So this is finite. But then this is given to you. So you, what you prove that expectation mod x square is finite. So uh, so therefore you did not prove the, I have, what I have to prove? I have to prove expectation of mod x is finite, right? Correct? Hello.
Yes, sir. Yes,
Uh,
sir.
uh, so therefore, this will mm, this will not because you did not prove the what we have to do, right? So this will not uh, do, correct? So what we have to do? What you, I have to prove what? I have to prove this is finite. Expectation of this finite. So I have to prove expectation of uh, this quantity is finite. Correct? Right? Now this
Yes.
one
Yes, sir.
I can write it, correct? Okay.
Yes, yes, sir.
So now I can apply the Cauchy Schwarz, right? Sorry. I can apply the Cauchy Schwarz. Hmm. Second. Yeah, so this is half into expectation 1 square equal to the power half. And this fellow is one, nothing but one, right? This is this is nothing but one. So so this is equal to expectation and something is L2 means this, right? So yeah, so this is given that this is x is in L2 is given to you, so this is finite. Now now it is done. Right? So therefore, expectation of mod x is finite. Yes, this is in L2 given. So this is finite. Given x belongs to L omega f. So therefore this is finite. So now expectation that so x is expectation also this implies x is in L1 omega. So what you tried is okay, but you have to do it just that you take the y as 1. ठीक है? Okay. Um, yeah. Now, so this is one thing. Now we will now we'll do something else. Is called conditional prob. I mean, you people have done it already. So, uh, you have done it already. Just so suppose you have two events, right? A, B belongs to F, so means two events, and probability of B not equal to 0, right? Then probability of A conditioning over B is defined as probability of A intersection B by probability. Yeah. This is conditional probability. You can know these things. Conditional probability. And then there is and then there is what is called the Bayes rule or the total probability formula. So this is also important. Total probability formula. You always have this probability space omega fp, right? A is an event, and there is a sequence, right? I belongs to, and this is also even. Okay. And these are pairwise disjoint. So such that BI intersection BJ is empty set for I not equal to J. Okay, so pairwise disjoint. So, such that it is pairwise disjoint, and you will have intersection I belongs to N BI is equal to omega. So that means omega is partition. I mean, so this is disjoint sets if it divides omega in uh, if you divide it in disjoint sets, so this is called the partitions. So you will have this thing. You'll have the partitions, okay, and so this is actually this is called the partitions of omega. So you partition omega in BIs. I mean, so it in a sense, simple sense that if you have omega, this is your omega. Suppose this is B1, B2, and B3. So it is fine. B1, B2, B3. So you have union, and here I am telling the countable union. So it is more little bit more general, right? I mean, you partition omega in something in some this thing. Okay, so it is then you can write it then probably okay, and another point is just another point is uh, probability of BI is not equal to 0 for all I. Okay. And then you write then probability of uh, so this is the this thing. This is the total. This is also called the base theorem. So base formula. I think you know this thing, base formula. Have you heard of this base formula?
Yes, sir.
Yeah. So this is the base thing. So, yeah, the proof is not that difficult. You can see the proof next time. Yeah, probably we'll see the proof next time. Have the proof next time. Anyway, yeah, so we will have our next class Thursday, and then we will see. Then we'll have 2 weeks off. Okay, thank you. Thank you.
Sir, thank you, sir.